Hello, welcome back. It's been a minute since I've had to do a new video, but we had to change some stuff up with using Hampton, and so that means that my notes 1E, 1F have been blended into just one thing of notes, and we're calling it periodic table. So if you have not already, please go ahead and do the quick review there at the top, this part up here. Go ahead and do that quick review there at the top. Pause the video and do that, and then come back so that you can get the answers. Pause. Are you paused? Okay. See you in a minute. All right. Welcome back. Good job. So, the parts of an atom are the proton, the neutron, and the electron. The proton has a positive charge. The neutron is neutral. And electrons are so negative. Oh my God. Ew. I know. It's dumb. But as I've said before, the dumber it is, the more likely you are to remember it. The protons and neutrons are found in the nucleus, and the electrons are in the cloud. Protons, neutrons, and electrons are called subatomic particles. Okay. You know the drill. Pause it if you need to. I'm moving ahead. All right, the periodic table. Remember how we talked about the periodic table? We talked about this table of elements that lists all the different ingredients in the universe. So, how many different ingredients have scientists found so far? So, right now, the answer is 118. And I'm going to say about 118 because technically in the hadron collider you could keep making elements, but what we've realized is the bigger they are, the more unstable they are, and some of these elements, even the ones that we say we've discovered so far, the ones that are 115, 116, 117, 118, all of those are so big and so heavy and so radioactive and so unstable, they only last for that long anyway. So to make anything much bigger probably wouldn't last long enough. Now, out of these, 92 are naturally occurring or can be found in nature. Everything else is either man made or only the tracest of trace amounts are found in nature. The rest of them are synthetic and had to be made by scientists in a laboratory. We also learned that the number of protons in the nucleus determines what kind of atom it will be. So, looking at the periodic table, now I did print, it turned really blurry. I don't know why it is so very blurry. It was a much better picture when I put it in the notes to start. So, yeah, but that's a wide periodic table, and that's basically what the periodic table is supposed to look like. These two rows right here get taken out and put below the periodic table as the lanthanides and the actinides, and then all of this just gets moved this way, and that's the periodic table you're used to looking at. But looking at a periodic table here at home, I recommend going to ptable.com. That's PTABLE.com. And you can use that one. The atomic number is that number that's above the nucleus. I don't know what I do with the periodic tables. Hang on. Oh, here they are. I hit them from myself. Maybe I'll edit that out. Maybe I won't. We'll see. So, periodic table. I'm going to zoom in. Ooh, periodic table. So the number that's up in that upper corner is the atomic number. And most of the time it's at the top on periodic tables, but sometimes it's at the bottom. The point is that it's the whole number. So that whole number, not the one with the decimal amount, but the one with the whole number, that's the atomic number. It tells you the number of protons in the nucleus of the atom. So I want you to pause the video for a second. Use that periodic table. Go to ptable.com, or maybe by the time you're watching these notes, you already have a periodic table that I've given you in your notes. But use that periodic table and find the atomic number, the whole number, the one that's not a decimal, and tell me the number of protons in each of those atoms there. Pause and do that. Pause. Okay. All right, welcome back. Here we go. Oxygen's atomic number is 8, so it has 8 protons. Helium's atomic number is 2, so it has 2 protons. Carbon has an atomic number of 6, so it has 6 protons. Radium, I don't have memorized. Should, though. It's 88. Xenon is 54. Indeed, 54. And potassium is 19. So, what would happen to a chlorine atom if it lost a proton? So, chlorine is up there. It's a halogen in family 17, and it has 17 as its atomic number. It has 17 protons. So, what would happen to it? It would now have 16 protons. Would it still be chlorine? Exactly. It would become sulfur, which is number 16. Which makes sense. If you lose a proton, the number's going to go down by 1. There is decay where atoms lose protons. And that's the worst kind of radiation. Does the most damage. All right, so what would happen to a hydrogen atom if it gained a proton? So this is what happens to hydrogen atoms in the sun when the process of fusion occurs. So we have one hydrogen plus one hydrogen that gets slammed together. We now have 2 protons. Is it hydrogen anymore? Exactly, it's now helium. So it would become helium. And that's number 2. All right, pause it if you need to. I'm erasing. Atoms are stupidly small. We can't see them with our eyes. We can't feel them with our hands. So scientists have had to come up with some incredibly small units to measure the mass of and volume of an atom. So can I use a triple beam balance or a scale to find the mass of an atom? Well, no, because air rests on it all the time and it doesn't register anything. So it's obviously not going to measure an atom. All right. Well, what about a yardstick? Can I use a yardstick to measure? And I need a yardstick. Excuse me while I go get one. Okay. So could I use a yardstick or a meter stick to measure the size of an? Of course not. It's too tiny. All right. So the scientists came up with the AMU as the unit for the mass of an atom. So 1 AMU is the mass of 1 proton or 1 neutron. So 1 AMU, protons and neutrons have the same mass, they weigh the same, and it's 1 AMU. That's the rate. So the radius of an oxygen atom is 60 picometers. Okay, Ms. Harris, so what the heck is a picometer? All right. Come along with me because this is crazy. All right, so here's our meters along the top, right? And the space right there, hang on, let me get it. The space right there between my fingernails. That teeny little space right there. Imagine in your mind dividing that up into a billion with a B, billion equal pieces. Got it? So that teeny little space, a billion equal pieces. 60 of those pieces is how big an oxygen atom is. Yeah, pretty crazy. That's small. So protons and neutrons each have a mass of 1 AMU. The electron mass is so small we can ignore it. Okay, so how stupidly small must electrons be if we've given a unit to the proton and the neutron, which, I mean, the atom is so small we can hardly comprehend it. And then the protons and the neutrons inside of it are even more ridiculously small that we can't comprehend, but they're still big enough to get a unit for their measurement. And electrons are so small. So how small, like electrons are like nothing. Anyway, the average atomic mass number of any atom is the decimal figure in the box on the periodic table. So when you look at one of the boxes on the periodic table and you look at that number that's underneath, typically it's going to have a decimal. And that's because it's the average. Okay. So just like when they do a census and they say everybody in the United States has an average of 2.5 children. Well, nobody has half a kid. That's not a thing. Just some people have 3 kids and some people have 2 kids, and it averages out to 2.5. Right? Same thing here. There's no atoms that have partial anythings. But when you take all the different isotopes of an atom, so I can have 5 carbon atoms and they all have different numbers of neutrons. They all have 6 protons, and that's what makes them a carbon atom. But this one has 5 neutrons, and this one has 4, and this one has 7, and this one has 6, and this one has. And so all of those, you average all those different ones together, and you get the atomic mass number, and that's why it's a decimal. That's why it's averaged. Um, I used to have a sheet to show y'all that as well. Hang on. Okay, so honestly, I probably should have filmed that because me coming through the closet door with this thing might have been pretty funny. But this is a chart of the nuclei. And so it has literally every single element, even the isotopes. So maybe I can get zoomed in enough. If you look across the top, you can see that is, which one are we looking at? Is it hydrogen? Do we manage to get, I know it is number 34, selenium. So this is selenium, all the different isotopes of selenium. So you take all of those different masses and average it together to get the mass number. So I want you to either go to ptable.com, or again, if it's been long enough and you're just now looking at this, you might have one of these from me by now. But look at the periodic table, look for the decimal number. It's usually going to be the number that's under, and tell me the atomic mass of each of the same elements that we looked at before. Again, I want you to pause and do that, and then come back and check your answer. Pause. Okay. All right, welcome back. Here we go. So oxygen, we're going to round it up to the nearest whole number. So oxygen actually already says 16 on the chart I'm using, so we're going to use that. Helium is 4. Carbon is 12.01, so we're going to round that down to 12. Radium is 226.03, so we're going to do 226. Xenon is 131.29, so we're going to do 131. And potassium is 39.10, so 39. Did you get them all right? Good job. The simple way to calculate the atomic mass of any atom is to add up the protons and the neutrons in its nucleus. Why don't we add in the electrons? Right, because they are so small, we can ignore them. All right, again, if you need any of this, pause it. I'm clearing it and moving on. Every element in the periodic table of elements has a code to represent its name. The code either has 1 or 2 letters and is called the chemical symbol for that element. So I want you to tell me the periodic table here. I want you to tell me what's the atomic number, what's the chemical symbol, and what's the atomic mass. So I want you to do this because all periodic tables are not made the same. Some of them move things around. The atomic number isn't always in the middle or on the top left or whatever. So that's atomic number. That's the symbol. That's the mass. So I want you to do that to the other two. If you're doing it digitally, you can either open this up in Cami or just add lines and then add text. Pause. Okay. All right, welcome back. Here we go. Yep, this is a number. This is symbol. That's mass. That's number. That's symbol. That's mass. Got it? Good. All right. Now we're going to look at the periodic table again. In the 1860s, there was this Russian scientist named Dmitry Mendeleev, and he was 13 years old. It makes me feel a type of way. I'm sure it makes y'all feel a type of way because that's how old you are right now. He was 13 years old when he started to figure out that the elements that had been discovered, and there were only about 60 discovered at the time, he figured out how they should be organized. I mean, haven't you ever wondered why the periodic table looks the way it does? Why it looks like this and not like in a straight lines or in a square rectangular table? It's because he figured out, even though there were elements that hadn't been discovered yet, he knew like there was a hole in the periodic table where he knew that an element would go because he had already figured out that these go here because they're related and blah, 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 blah. And what he literally did, and the reason why the periodic table looks the way it does, he invented it, he put it together, was he made a little card, and of course it didn't have atomic number at the time because they didn't know that. But they had a little card that had the information about it on it, and he just laid them out on the table and organized them around. And he started to notice some patterns. Now, the first pattern in the periodic table, oh, PAVE. The acronym PAVE will pave the way for you to remember the patterns of the periodic table. So the P in PAVE just stands for patterns. It's just supposed to remind you that patterns is what we're studying here. So the first one is atomic number. It's by ones. It's not much of a pattern, but it's a pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, all the way to 118. That's a pattern. A boring pattern, but a pattern all the same. Then the valence electrons have a pattern. Everything in family 1 has one valence electron. Everything in family 2 has two valence electrons. Now, the transition metals don't follow this rule, and you don't have to know what transition metals do until chemistry, so don't worry about them. Just know that these are metals. And then we get over here to family 13. Now, we skipped 10 here. What's 13 minus 10? 3. That's right. So everything in family 13 has 3 valence electrons. Everything in family 14 has 4. Everything in 15 has 5. 16 has 6. 17 has 7. And 18 has 8, except for helium, because helium doesn't need 8 to be full. Helium and hydrogen only need 2 to be full. But everybody else has 8 valence electrons in that column. So the pattern is 1, 2, skip a few, 3, 4, 5, 6, 7, 8. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So 1, 2, skip a few, 3, 4, 5, 6, 7, 8. And then lastly, energy levels. Everything in the top row has 1 energy level. Everything in the second row has 2 energy levels. Everything in the third row has 3 energy levels. Everything in the fourth row has 4 energy levels, etc., etc., etc. So by period. What do I mean by period? Well, period is horizontal. Group or family are vertical. Yes, I would write that down if I were you. All right, pause it if you need to. I'm moving ahead. Look at Dimitri. He was one heck of a beard. All right, so that's cool, but what does it mean? Let's look how the periodic table of elements shows us these 3 patterns. The chemical properties. What does the P stand for? That's right, patterns in the periodic table. What's the A stand for? That's right, atomic number, or the number of protons in the atom. What's the V stand for? That's right, the valence electrons. Those are the electrons farthest from the nucleus, those outermost electrons. And finally, energy levels. The period gives you the energy level. Going once, going twice. Oh, listen to me like I'm in class. Y'all can pause it if you need to. Chemical properties of a substance tell us how they will react or interact with other substances. The V in our acronym tells us why elements in the same family act in similar ways. So everything in family 1 all acts the same, and that's why those alkalis are extremely reactive. They're highly reactive. Halogens are extremely reactive for a different reason, but they're all together because they all act the same. They act in similar ways because they have the same number of valence electrons. These outermost electrons are critical in determining how the atom will react when it comes in contact with other atoms. Noble gases are very stable, which means they don't often react or bond with other elements. It's almost like 2 full balloons bumping into each other. There's just nothing to be done, and so they just keep going. They've got that full valence energy level. Since it's full, there's no need to join or bond with other atoms to make them the outer energy level full and make them happy. And so, they don't bond with anything. It's only the things that have missing electrons or electrons to give away that have that full outer energy level. All right, again, pause if you need to. All right, so let's draw what this looks like. So if an atom only has 1 energy level, it's full when it has 2 valence electrons. So helium has 2 protons in the nucleus, and then it has 2 electrons in its outer energy level, and it is full and happy. It's stable. This is the periodic table, noble gases. Stable. Halogens and alkalis react aggressively. Good job. All right, so neon is also a noble gas, but it's not in row one. So just two won't be enough. Neon is going to need 8 in that outer energy level for it to be safe. So neon has an atomic number of 10. So it's got 10 protons in the nucleus, and then it's got 2 electrons on the outer energy level, and then 8, or on the outer, on the energy level, and then 8 on the outer. 1, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, 8. Great. And then finally, sodium, an atom like sodium, gives away its. Oh, oops. Didn't mean to do that. You just vanished. I don't know how to bring you back. Um, I fix it. I figured it out. Okay, sodium. Sodium is an alkali. So sodium is here in family 1. So there's sodium Na in family 1. So that means it has 1 valence electron. Well, it very much wants to get rid of that valence electron. So it has 2 here on the energy level, and then 8 here, 3, 4, 5, 6, 7, 8. But then it very easily gets rid of that 1 electron that it has. That goes bye-bye, and this becomes a positively charged ion because it has only 10 electrons, but it has 11 protons. And so we end up with sodium that has a positive charge. And we'll talk more about that later. All right, again, pause if you need to, erase it. All right. It would be a giant pain to have to complete a drawing or an electron configuration every time you want to know the number of valence electrons. So, like I've told you already, there is an easy way to remember it. Do want to show you what the electron configuration would look like for oxygen, but we're not going to go into it. It's not going to be on the SOL. I used to spend days on this, and I just don't feel like I can. So, if you take chemistry in high school, the videos for when I used to teach this are on the YouTube channel. I've given you bit.ly links, Homes for Puppies 1 and Homes for Puppies 2. If you're ever in chemistry and you remember, I highly recommend watching it. I've had multiple students say that I teach it in a way that makes sense. But you take the 8 uh, oxygen is going to have 8 electrons. So it's like 8 puppies you got to find homes for. You go out into the neighborhood, you go to the Smiths. The Smiths will take 2 puppies. So we've taken 2 puppies out of our basket. There's no more houses on that street. So then we're going to go to 2nd Street and the Smiths, and they take 2. Well, now we still have 6 puppies in our basket. So now we're going to go next door to the Petersons. The Petersons will take 6, and we don't have 6 to give them. Because oxygen has 8, and we've already given away 4. 8 minus 4 is 4. So we only have 4 puppies to give them. I know that seems weird, and I promise it will make more sense if you ever do watch the videos, but you don't have to know it for the SOL, so don't worry about it. And then the way you would figure out the valence electrons is that outermost energy level added up. 4 plus 2 is 6, so it has 6 valence electrons. All right, so the periodic table can help us out. The family number, except for the transition metals, because I've told you already, the transition metals don't follow the rules. The family number, besides the transition metals, can tell you how many valence electrons are in the element. So everything in family 1 has 1. Everything in family 2 has 2. Everything in family 3, 4, 5, 6, 7, 8. And family 18 has 8, except for helium, which of course has 2. So I want you to take a minute, please, and tell me how many valence electrons each of those has. Again, pause it. Pause it. Okay, welcome back. Here we go. Hydrogen, yes, 1. Carbon, yes, 4. Argon, yes, 8. Lead, that's what Pb is. Lead, I gotta find it. Lead, yes, 4. Calcium, 2. There's calcium, family 2. Oxygen. We just did this one. Oops. 1, 2, 3, 4, 5. It is 6. Yeah, 4 plus 2 is 6. Duh. And aluminum is in family 13. 3. Okay. Pause it if you need to. All right, those red dots. Those red dots are called Lewis dot diagrams. Lewis dot diagrams, and are a quick and easy way to show the number of valence electrons that any element has. So let's draw a couple of them. Generally, you draw the dot starting from the top and then go around in a clockwise motion. Starting from the right side and going around in a clockwise motion. So sodium's in family 1. It has 1 valence electron. Carbon is in family 14. That's right. So it has 4. So we're going to go 1, 2, 3, 4. And this is one of the reasons why carbon is in everything. Carbon wants to bond with everything. It's like carbon has hands out on all 4 sides going, come on and join with me, guys. Carbon likes to join with itself, especially in making these long carbon chains. And that's what we're made out of. That's why we're considered to be carbon based. All right, oxygen. We're going to do 1, 2, 3, 4, and then 5 and 6. Argon is in family 18, so it has 8. So we might as well just go ahead and draw 2 on each side because that's what it needs. Aluminum is in family 13, so it has, that's right, 1, 2, 3. Where's chlorine? Right, it's a halogen. It's in family 17. So how many? 7. So this explains why chlorine wants to bond with stuff so much, because it only needs 1 valence electron. So that's why it's so unstable. And then potassium, yep, also in family 1. So it has 1. All right, so this quick little review down here. Valence electrons are the ones in the outermost energy level. And they determine if the atom is reactive, stable, or somewhere in between. And I bet I meant for that to say stable / reactive because of how long that line is, but it doesn't really matter. Thanks for sticking out with me. Have a lovely day. Make good decisions. Bye.